This program is brought to you by the University of California, Davis on iTunes U. For more information, please visit us at itunes.ucdavis.edu.
So we talked a lot about those cubic splines and different ways to specify these degrees of freedom. And for each cubic spline, the way I'd set it up, there are two end conditions, right, that you can choose freely. In the case of a so-called open spline, when you have the spline not going back to where it started, right? And the one case I have not talked about yet is the case, well, when you do not have these 2 degrees of freedom left over, but they are taken care of, namely by forcing or requiring the spline to end where it starts. Okay, so that's the periodic spline. So the problem then is the following, and I'll start with a sketch. Again, I give you the answer. I give you a configuration of a periodic spline, cubic spline, the way it looks like in terms of its D points and then the Bezier points and the parametrization. And I will put the linear system on the board, how the linear system should come out for this case that is the periodic case or the cyclic case. So an example. So let me put this one on the board. Okay, so I come back to where I start from, and the numbering scheme, I guess, was like this. So this is a double D point. So this is this point D0. Then this one will be D1. This one is D2. Here we have D3. And those are the unknown control points that we will solve for later on. And a few more. And this is now the periodic condition that this first control point, D0, is the same as Dn. So this one is Dn minus 1. And this is Dn minus 2. And so forth. What else do we have? So there was a parametrization, of course. And I called this U-line. And how many segments will I have? Probably should give you the configuration first. So there are Bezier points here. There are 2 Bezier points here. Two interior Bezier points for each of these original line segments. And then there are these additional polygonal elements that connect Bezier points like this. Okay. And then the original points that we actually start from are the bullets. So this would be point 0. This would be point 1. This would be point 2. And so forth. So this guy would be point n minus 1. This one would be point n minus 2. And this one would be point 3. Okay. So I said those ratios are essential. What ratios? The ratios that define the parametrization. How many curve segments do I have? In this example, 1, 2, 3, 4, 5, 6. 6 segments means there are 6 intervals here, relevant intervals. 3, 4, 5, 6. And then I needed these additional ones, 2 to the right and 2 to the left. And I give these knots, those are called the knots, names. So this would be U0, U1, U2, U3, U4, U5, U6. Well, I should not do that. I should say this is well, I can't. That's not the numbering we used, right? We started numbering starting at 0, where the first point is. So point 0 goes hand in hand with U0. So this is U1, U2, and this is U3. And then I end with, what do I call the last one? The last one I call P0, but P0 is also Pn, because that's the period. 0, 1, 2, 3, 3, and the next one is n minus 2. U sub 3. un minus 2, un minus 1, and un. Okay, so we have 6 intervals here. So I make these intervals bold. And these 6 intervals will later on correspond to 6 segments. And then we have these 2 additional ones to the left, 2 additional ones to the right. So if this is u0, this must be u minus 1, and this is u minus 2. And this would be un plus 1, and this is un plus 2. Okay. The only thing that matters is the ratio of these length of these intervals. So this is delta 0, the length of this interval. This is delta 1, this is delta 2, this is delta 3, this is delta n minus 2, this is delta n minus 1. This would be delta n, and this would be delta n plus 1. I come back to that because there is a periodicity constraint, of course. So this is delta minus 1, and this is delta minus 2. Now I will change this. Why? Because I start here, I run around, and I come back. And this periodicity constraint also has to be reflected by the spacing of these u values. So these deltas repeat themselves also by going around. Okay? So un corresponds to point n. But point n equals point 0. So the deltas repeat. That means after delta n minus 1, I have delta n, but delta n has to be delta 0. Okay? So that's why I bring this out here. And the important point here is this is delta 0, and this is delta 1 again. It repeats itself. The same here. This is the ending of the curve. So this delta minus 1 is also delta n minus 1. And this is delta n minus 2. Okay. And why? Because this parameter line is also wrapping around and repeats itself, right? So these are the periodicity constraints. Periodicity. Where do these go? Well, we always have 3 ratios per line there. So this is 0.0 first segment. So this must be delta 0. This is delta 1, delta 2, delta 3. Delta n minus 2. This is delta n minus 1, and so forth. So delta 0 goes hand in hand with, well, how do I have to wrap it around? Delta 0 goes hand in hand with delta n minus 1, and this must be delta 1. This must be delta 0. This is delta 2. This is delta 2, this is delta 1, delta 2, delta 3, and so forth. So you see how these ratios are mapped onto these segments. And then we have 2 ratios mapped onto these inner line segments. So here we would have delta 0 to delta 1. Here we would have delta 1 to delta 2, and so forth. Finally, when you compute the curve segments, you will get this picture. Right? Here are the individual segments that later on will come out. Where are the Bezier points? Well, this is also the first Bezier point. This is B0. This is Bezier point B1. This is Bezier point B2. This one is Bezier point B3. This is Bezier point B6, and so forth. So the last one also has to be Bezier point B3n. Okay. That's how the scheme goes. There are no degrees of freedom. Everything is taken care of by the requirement for the curve to close back onto itself, and ensuring or requiring that the curve at this double point here has the same position, the same derivative, and the same second derivative. Okay, because you require that, you have no degrees of freedom left. Now there was a linear system. What does a linear system look like? What does the linear system look like? in this case. And so I just put this, I put just one row onto the board, and from that we will see the matrix. In general, we had an equation, and I use these abbreviations. We had something that I called an alpha I value times a d point, di minus 1, plus a beta I value times a di plus a gamma I value times di plus 1. And on the right-hand side, I had some kind of weight I times the point that is given there, point I. That was a general form of a single condition for one junction. Okay, now what are the unknowns here that we have to solve for? Again, this is a solution to the problem. What's given? The input are the points, 0, 0.1, 0.2, 0.3, and so forth. From the points, you decide on what type of a parameterization you would like to choose or use. You compute this parameterization. And once you have that, then you have to set up your linear system of equations and you solve it. And you solve for what? You solve for the unknown d's. The points p are given. The control points d are unknown. And one particular equation looks like this. And how many equations do we have to write down for this? Well, it starts with I equals 0, right? For point d0, that's the first unknown. d0, d1, d2, and we have to go all the way up to dn minus 1. We do not have to write down the equation for dn because dn equals d0. So how many equations do we have to write down? N. The first one for index I being 0, and the last one for index n minus 1 makes a total of n equations. So I write those down, and then I write them in matrix form. In periodic case, what does it look like? So the first equation is, well, here this I is 0, d0. Right? So I have something like beta r0 times d0. Okay, and then something here. And then here is my gamma 0 times the next point is d1 equals weight 0 times point 0. Okay, what does go here? This is times d. What is this? d0. What is the point before d0? The point before d0 is d minus 1, but d minus 1 is dn minus 1, right? That's the point before it. Huh? d0, the one before it, is dn minus 1. So this is dn minus 1 times alpha 0. That's the first equation. And the next equation, I can also write the next one down. So the index now is 1. Beta 1 d1 plus gamma 1 times d2 equals weight 1 times point 1. Okay, so what goes here? This is alpha 1 times d0. Okay, so what is the last equation that I have to consider? The last equation is the equation that goes hand in hand with this guy, dn minus 1. So I is n minus 1. So the last equation is beta n minus 1 times d n minus 1 plus something there plus something here. What is it? It is plus gamma n minus 1 times dn plus 1. The next one is dn, but dn is d0. Okay, so the periodicity says this is times d0 equals, what is it? Index is n minus 1, weight n minus 1 times p n minus 1. Right? That's the last distinct point that I had specified. What goes here? Here is alpha n minus 1 times what? D n minus 1. The one before is the n minus 2. Okay, so this is the periodic form of this linear system of equations we have to solve. How many unknowns? How many equations? We have d0, d1 up to dn minus 1. We have n unknown d's, and we have n equations, right? N unknown di's and n equations. So this is great. because we can solve that. And now I should also put the system of equations on the board for this particular case. All right, so I just write the same thing in matrix form, or in matrix form. All right, I have this huge matrix. What is the unknown vector? The unknown vector is a vector of the unknown d's, and it goes d0, d1, and the last one is dn minus 1, and before is dn minus 2, equals on the right-hand side. What is it on the right-hand side? I have my weights, weight 0 times 0.0, weight 1 times 0.1, and so forth until weight n minus 2 times point n minus 2, and weight n minus 1 times point n minus 1. All right. How about the elements, components of the matrix? Well, I just put this into the matrix. Okay. What is it? B0 times D0. This is D0. So beta 0 goes here, right? Beta 0, and then plus gamma 0 times d1. Here is d1, so the gamma 0 goes here. And then the alpha 0 multiplies the dn minus 1. Okay, so the alpha 0 goes here into the last cell here of the first row. Alpha 0 goes there. Huh? Okay, so what about the second line? So it's alpha 1 times d0. Alpha 1 goes here times d0 plus beta 1 times d1 plus gamma 1 times d2, and so forth. The last row, what do I have in the last row? It's beta n minus 1 times dn minus 1. So the beta n minus 1 goes here into the lower right corner, beta n minus 1. Before it, I have times dn minus 2, and the factor is alpha n minus 1. So the alpha goes here, alpha n minus 1. And now comes the periodicity constraint. The gamma n minus 1 multiplies d0, so the alpha n minus 1 has to go, the gamma n minus 1 has to go into this lower left corner. Gamma n minus 1. Okay. Right, and just to show the structure, I also put the second last row down. The second last one has to look like this. There's a gamma here, gamma n minus 2. Here is beta n minus 2, and here is alpha n minus 2. Okay, and now you see the beautiful structure. There is a main diagonal with all the betas here. Then there are the two off diagonals consisting of the alphas and the gammas. Okay, and now, due to the periodicity constraint, we have these two isolated guys living in the upper right and lower left corner. Okay. Okay. So this is the so-called cyclic tridiagonal matrix. Okay, it is cyclic because, well, these upper right and lower left corners have entries different from 0. So this is a cyclic tridiagonal system. Cyclic tridiagonal system. Now, can you run this system directly through your tridiagonal system solver? Directly, no, you can't, because the particular tridiagonal system solver I gave you expects that all of this is 0 and all of this is 0, right? So again, for this particular case, you have to do some additional standard Gaussian elimination steps to make sure that your force is 0 there and your force is 0 there, right? And you can do that by just linearly combining first row and last row and first row to force a 0 in these corners. Okay, and then you have it in the setting for the tridiagonal system. And of course, all the other ones here are 0, and all the other ones are 0 there. Okay. So again, you can also solve this in linear time once you have brought it to tridiagonal form, which you can do. And once you have solved for the d0 up to the dn minus 1s, of course, at the very end, you state dn is d0, right? That is built in. So you have that. And now I give you the system for the specific case when you use an equidistant uniform parameterization. Then this takes on a very nice and simple form. And it's an easy test case for you to test and debug your program, whether your system solver and your evaluator and your entire framework can handle this and produces a case, produces the right solution for a uniform equidistant parametrization. So a special case that's the uniform equidistant parametrization. That just means that all of these u sub I values, u sub I, are set to I, okay, are integer values. So the spacing is always 1. All the deltas are 1. What does the system become in that case? The system becomes this one, 4, 1, 1, 1, 4, 1, 1, 4, 1, 1, 4, 1, and so forth. You have a bunch of 1s, you have a bunch of 4s in the main diagonal. 1, you have the 2 off 1s in these corners. And you have your unknown vector of d's, d0 up to dn minus 1. And on the right-hand side, you have, what does it become? It becomes 6 times p0 up to pn. Okay. Very easily remembered. So if you want to get a very simple, straightforward answer to the problem of interpolating a bunch of points, these points, with a periodicity constraint, right? First point equals last point, then you can force the initial parameterization to be uniform equidistant, and the answer that you get will be the cubic spline looking like that. Okay, and here's a system for that. Is it clear so far? Is it clear? Makes sense? Okay. And this is, in fact, the system that you often see in many textbooks when people talk about cubic splines and periodic cubic splines. You will see that they implicitly make this assumption that these parameterizations are uniform and equidistant, blah, blah, blah. And you will see these numbers, 1, 4, and 6. And so that's where they come from. All right. So now we have talked about the three most important ways to specify end conditions, namely specifying the two end derivatives, right, derivative vectors, or forcing the curve to end like a straight line, i.e. setting the second derivatives to 0, the natural cubic spline, minimizing some means of energy. And then this is a natural cubic spline, okay, also minimizing the energy, actually. The cyclic one. Okay, so there's one difference that you might have seen between the equation that I put on the board and the equations that are in the book by Farron. They're different, right? The matrices look different. These expressions with the deltas. And the equations between the ones in Farron's book and mine are due to the fact that Farron uses what is called multiple end knots. I have these parameter values, u sub u minus 1 and u minus 2, that are outside the domain, right? And then un plus 1 and un plus 2 outside. And he forces those values to coincide with the values of u0 and un. Okay? By forcing that, you have what is called multiple end knots. And so I only want to sketch briefly what that means geometrically, and so you have an understanding for the differences between the presentation in the book and my presentation. My presentation is just a generalization of what the book talks about. Okay, so the book is a special case of what I've put on the board. So using so-called multiple or triple in this case, triple end knots. Just want to explain this for a particular configuration. 1, 2, 3, 4, 5. Okay. So here are some D points. Don't care really about the ending here, I only care about the beginning. And here is my parameter line, U. This is my D0. This is an open case. This is D2. This is D3. And D4, and so forth. And I illustrate only at the left end, at the beginning D0, what happens when I introduce these multiple or triple end knots. You remember that somewhere I have these values, right? And I called them U0, I call it U1, I call it U2, I call it U3, and so forth. And then I had these additional helper values outside, U minus 1 and U minus 2, U minus 1 and U minus 2. And the spacing between these deltas was reflected or was mapped in the same ratio onto these line segments. Now what Farron does, he uses at this location U0 a triple end knot. A triple end knot means that the values of U minus 1 and U minus 2 are equal to the value of U0. So you have in your program 3 times the same value, like 0, 0, 0, 3 knots on top of each other. Okay? So I cannot draw that, but I can indicate that by putting these two helper knots very, very close, infinitesimally close to U sub 0, right? So I can put these helper knots very close. In the limit, they will become the same. So this is there, U minus 1, and there is U minus 2. Again, the limit case is I make them coincide with U0. But for the construction, I still have to consider these deltas. Now, that also means that these two deltas here at the end become 0. Okay? So this is my first delta here. This is delta 0. This is delta 1. This is delta 2. And then I have these very, very short deltas, which ultimately become 0 and collapse. So here is my delta minus 1. And here is my delta minus 2. And they, in the limit, will go to 0. And this guy, will go to 0. And in the limit, these three values will become the same. What does this mean when I map these ratios 0, 0, something onto this segment? 0 to something, that means that everything is pulled into this lower left corner, right? So that means I have the first 2 points here, right? What else? I have to map the next 3 ratios onto the next line segment. That is 0, 0 to delta 1. Okay, so I have something like this. Okay, and then comes actually the split delta 0, delta 1, delta 2. Delta 0, delta 1, delta 2. Okay. And then this is how to get to the p's, the points, from the actual squares, from the d's. Then in the construction there was this connecting line segment from the last one here to the first one there, and from this one here over to there. And then it continues like that, right? Where were the original points? The original points are these guys. What happened here? I've pulled everything. What happened? Huh? I've pulled everything down here, right? So, connector, point, and this point gets also pulled down, right? So this one gets pulled down there. Huh? This is a limit case when these two deltas become 0. You have to think about that. So, okay. So this is the first point, P0. This is point P1. Okay. And so the first segment looks like this. That is the first cubic segment. Where the Bezier points, this becomes the first Bezier point, B0. This one becomes the second Bezier point, B1. This one becomes Bezier point, B2. And this one, point 1, becomes Bezier point, B3. So we have 1, 2, 3, 4 Bezier points for the first cubic segment. And due to the fact that these two deltas shrink down to 0, you have this beginning of the spline. Okay? And when you set things up in this way, and you say delta minus 2 equals delta minus 1 equals 0, then you get the linear system that is in the book by Farron. Okay? And then the cubic spline curve actually passes through the point D0. Okay? So that's the difference between the book and my annotation. Only that you have heard where that difference comes from. Okay. The next topic is a very fundamental topic. The next topic will be about, any guesses? What comes next? I talked about cubic splines, and now I talk about, what's the next topic? B-splines, right? B-splines. Why are they called B-splines? B stands for what? Tell me. No, we are done with Bezier curves, right? Bezier curves are now lying in the past. We're done with those. Now come B-spline curves. B stands for what? B-spline. Look it up. Okay, well, why are they called B-splines? I want to tell you. B-spline curves. So, have you read the chapter in the book already about B-spline curves? Are they better than Bezier curves, or more difficult, or worse? Nicer? What did I say about Bezier curves? Are Bezier curves good or bad? You want to design something, right? So if you design with a Bezier curve, just one, you want to design with one Bezier curve. For a Bezier curve, you always specify the control polygon or the control points, right? 4 control points, 1 polygon, 1 curve. If you want to alter the shape of your design, that means you want to modify or change 1 point, right? But if you pull 1 point and you move this point here, then what? The whole curve will follow, right? The whole curve will change. So in that sense, this Bezier representation is a global representation or a global scheme to design or represent something. Each point influences the entire curve, correct? So is this good or bad? If you were to represent the hood of a car by one huge patch, one huge Bezier patch, and then you want to change the hood a little bit, and you pull 1 control point, then what will happen? You change the entire hood. It's not good, right? Okay, so you want to have a scheme where you can pull a single little happy control point, and it only changes the hood, the bumper, the fender in a local area, right? So that's the main reason why we go from what is called a global scheme to a local scheme. B-splines can be introduced in good ways, in horrible ways, in geometrical ways, or in analytical ways. I will introduce you to all these different notations, but first I would like to get the nomenclature and the terms straight. Okay, so I will just start with putting a picture on the board to tell you what are the defining elements that constitute a B-spline curve. Okay, so we understand what the different pieces are. Next topic, B-spline curves. B-spline curves. So just B-splines, right? B-spline curves. Okay. And now we will see how everything comes together. These squares, the circles, the bullets, and how the basic curves are actually related to the B-spline curves. How one can transform one representation into the other later on. We will see that too. So I put an example on the board, and I give you a bunch of squares connected by line segments. So this is a polygon, and there is a number that I give you. I give you a number k, which is called the order of the B-spline curve. And here I would like to do an example where I say k equals 3. Okay, what does that mean? I have an order of k equals 3, and I have these control points, and they are the Boor control points, and I now start indexing them, starting from d0, and the last one I will call dn. Okay, so from now on, the first one will be called d0, no longer dn minus 1, and the last one will be called dn, no longer dn plus 1. What else? Okay, k equals 3. We will see what that means. Anyway, k equals 3 means I'm dealing with a so-called quadratic B-spline. Quadratic B-spline curve. So that means I will have a bunch of quadratic segments making up, in union, the entire curve. Where are these individual segments? Well, I can sketch them, okay? And so here's a first segment, here's a second segment, and here's a third one, and here's the last one. Okay? Okay. So all of these are parabolic arcs. This is D2, D1, this is D2, this is D3, and so forth. Now what else do we need? These are the individual segments. So there is a first one and there's a last one. The first one I call segment 0, right? Seg 0. The next one I call segment 1. So this is a segmented curve. Multiple segments making up the entire curve. What else? Well, each curved segment can be thought of as taking a piece of the straight line and bending it and deforming it. So again, we have the notion of the parameter line, and again we call it U. How many domain intervals, they are called, do I need? Gesundheit. For 1, 2, 3, 4 segments. For 4 segments, I need 4 pieces that are relevant here. 1, 2, 3, 4. Okay, and the relationship is as follows. The first of these domain intervals, this is a domain. The first one maps to segment 0. The next one maps to segment 1, and so forth. And now comes something that we have to get used to. For an order k equals 3, I will have to introduce 2 additional knots to the left and 2 additional knots to the right. Okay? 2 to the left and 2 to the right. And now comes the numbering. And again, there are different ways how to number these knots and how to index them. And I just choose one. I start now counting at 0 here. This is U0, U1, U2, U3, U4, U5, U6, U7, U8. And this particular chunk from here to here, that is called the domain of the entire curve, because these 4 intervals define the 4 segments of the overall curve. So this is called the domain. So what are these U sub I guys called? They are called the knots. Okay. So, and I have U sub I, the set of these U sub I values, and they go from I from 0 to n plus k. Okay. Here, what is n in this case? 0, 1, 2, 3, 4, 5. In this example, I have n is 5. Okay. So the last one is U sub n plus k, 5 plus 3, U sub 8. These are called the knots. Knots. These are the important words for the B-spline. The knots, the order, and the control points. These are the control points, the D0, D1, and so forth. They are the Boor. And that's where the D comes from. Here, D, the Boor control points. And that goes back to Carl de Boor. These are the defining elements for a B-spline curve of order 3. Now, there is this notion of segment, and there is this notion of order, and there is a notion of control point. There's one easy way how one can remember how this is related. K equals 3 means that each segment will be defined by 3 control points. Okay, again, very important. This is a fundamental behavior. Each segment is defined by 3, k equals 3, by 3 control points. No? Okay. That means this segment, for example, segment 1, is defined completely by D1, D2, and D3. The other D points have no influence on that. Okay. So that's why I make them now. I fill these squares in, okay, and I do an example. Segment 1 is completely defined by its corresponding 3 control points, namely D1, D2, D3. Same here. Segment 0 is defined completely by D0, D1, D2. This segment here, segment 2, is defined completely by D2, D3, D4. Okay? So each triple of consecutive D points defines uniquely one segment. Okay? So I can say this here more in example form. So I can say D0, D1, and D2. They imply completely segment 0. The first triple, k equals 3, triple, 3, imply segment 0. The next triple is D1, D2, and D3. And they define completely segment 1. And so on, okay? So that means D2, D3, and D4 define the next segment, segment 2, and so forth. Okay? That is the relationship between consecutive control points and the order. Now, the order is an arbitrary integer, right? K can be 3, 4, 5, 6, 7. And the more control points you would like to have an influence on a segment, the larger is k. The more local you would like your representation to be, the smaller k has to be. Okay. So now that we have the basic nomenclature on the board, I can give examples. What is the simplest B-spline, the lowest order B-spline? K equals, I jumped into a high number right away. Give me a smaller number than 3. K equals 1. It's an interesting B-spline, right? He says k equals 1 is the simplest B-spline. Okay, k is the number of points implying a segment. K equals 1 means that each segment is defined by 1 point. Okay, so you specify 5 points, boom, 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 boom. Each segment is defined by 1 point, no matter what. That's the definition. Then what is a curve? The curve is a set of those 5 points, not connected. That's correct. Is it the first meaningful curve? Maybe it is, maybe not. But so the first meaningful is really k equals 2. K equals 2 means 2 consecutive control points imply a segment. Now follow your intuition. What types of segments might those be? D0, D1, D2, D3. It is the original polygon. Okay, the original polygon that you sketch and trace out is the B-spline curve. It's just a polygon, piecewise linear, a bunch of line segments. Now the next one I put on the board, k equals 3. It consists of these parabolic arcs, right? And then we go to k4 and k5 and so on. So, all right. Examples. Okay. K equals, let me start with k equals 2, okay? I like the k equals 1, 2, but it's a boring picture. K equals 2 is, of course, the linear B-spline, right? The linear B-spline curve, but I just say B-spline. Of course, when I do that, that is the curve. D0, D1, D2, D3, D4. The control polygon is a curve. Control polygon is the B-spline curve. No matter how you parameterize that. Okay? Always get the polygon, regardless of how you choose your knots, your u sub I values. Next one is k equals 3. I have it on the board. I don't want to sketch that again. Okay, so you have always 3. Well, I can sketch it again. I should, and point something out so you understand what happens. 2, 3, 4. In the quadratic case, in general, you will have 3 points, control points, D0, D1, D2, D3, D4. You will have 3 consecutive control points control or define a curve segment, and the 2 endpoints lie on the original polygon. Okay? That's the important part. The 2 endpoints of each segment, quadratic segment, will lie in the interior of one of those line segments, as a rule of thumb. And the rest is a parabolic arc connecting them. Okay, that's why I could sketch it so quickly. So I say somewhere this thing starts on that line segment, ends somewhere there. Okay, so the curve has to look somewhat like that. So this is segment number 0. Then it will continue like that. Okay, it ends again somewhere in the interior of this line segment, and then it will end like that. Okay, so that is a quadratic B-spline. So this here is segment 0. This here is segment 1. Here, this is segment 0. And this is segment 1. Okay. Different people like to use different ways to index. Some people like to start at 0. Some people like to use negative indices. Some people like to start at 1. I mean, so different textbooks, different papers use different indices just to confuse you. But it doesn't matter, right, as long as you understand the concept. So this is a quadratic B-spline. Quadratic B-spline. And the insight is that the endpoints of each segment lie in the interior of a line segment of the original polygon. So segment endpoints, I just say lie on control polygon, okay? lie on control polygon. And now, again, comes the most important one. Linear, quadratic. The next one has to be called, what's the name of the next one? Cubic, right. And the important one is the cubic B-spline. And that is for k equals 4, the cubic B-spline. And now you will see the picture that you have seen before already in a different context. So k equals 4 means that 4 consecutive de Boor points, D points. Now it is clear why these D points have this D, why they are called D points for de Boor. So here is D0, D for de Boor, right? D1, D2, D3, D4, D5. How many segments total will the curve have for this example? K equals 4. How many segments will I have totally here? 3. Why? There's 3 sets of quadruplets, right? 0, 1, 2, 3 gives you the first segment. 1, 2, 3, 4 gives you the second one. And 2, 3, 4, 5 gives you the last one, 3. Okay, 3 segments. Where are they? They are no longer the line segments. They are no longer touching. They are somewhere else. Okay? So the first 4, D0, D1, D2, D3, give you a first segment. Now just sketch it. It has to lie somewhere here. The next D1, D2, D3, D4 give you the next segment. It has to look somewhat like that. And then comes the last segment. D2, D3, D4 define the last segment. Okay? So from here to there. So there are 3 segments. Okay, and they lie there. That's where they are. They do not touch the control polygon at all. Yes, they resemble the control polygon in a sense, but they are off. So here, this segment corresponds to this part of the control polygon. Right? And of course, again, the shape of the polygon mimics the curve. That's what you want. You want to have a scheme where the control polygon resembles the shape of the curve, right, that you design. That's why I use these schemes. Okay. And so here, the segments in general no longer touch the polygon, right? Segments in general no longer touch the control polygon. Touch control polygon. All right. So now comes one of the most important algorithms in this class, just as important or even more important than this de Castillo algorithm. So this next algorithm is the de Boor algorithm that is used to evaluate B-spline curves. These are the 2 most important algorithms, I guess, in the class. The de Castillo algorithm to evaluate a basic curve, and the de Boor algorithm to compute points on these curves, right? I mean, just this is by inspection, right? You still do not know how to write a computer program, how to compute a bunch of points on these curves, right? That's what you need to do for doing this next assignment, right? You need to compute points on the curve. How do you compute them? And obviously, this k has to go in there, these original control points go in there, and then the spacing of this parameter line, right, goes in there. How do you do that? And again, I just would like to teach the essentials of the algorithm by doing a specific example, right? I teach you the essentials of the algorithm by walking you through 2 specific examples, the quadratic case and the cubic case. And if you understand fully what I'm doing for those 2 cases, then you can use induction, right, and generalize to an arbitrary setting. Right? Only have to understand how this algorithm works for quadratic and cubic cases, and then all the other cases follow. So I start with a specific example for this de Boor algorithm. and we will jointly evaluate a quadratic B-spline curve. We will compute 1 point on a quadratic B-spline. How to do that? And again, there are multiple ways to do that. Some people like the algebraic way, just throwing a nasty equation onto the board, and then there's a geometrical way, doing it with a nice geometrical construction. So this is very important, the Boor algorithm. The Boor algorithm. Okay, and I want to teach you the algorithm by 2 concrete examples. 2 concrete examples. Quadratic and cubic. Quadratic and cubic cases. Okay. Okay. Quadratic case is k equals 3. What do I have? I have a bunch of control points, right? I name these control points, D0, D1, D2, D3, D4, D5. Somehow you have a means or oracle to specify these, to specify the parameterization or the parameter values or the knots. How many segments will you have for this curve? 3 consecutive points give a segment. 1, 2, 3, 4 segments, right? There will be 4 segments. That means you will have 4 of these relevant domain intervals, and we need 2 outside on this U line and 2 to the left. The numbering scheme, again, this is just choice. I start counting at 0, U0, U1, U2, U3, U4, U5, U6, U7, and U8. The 4 curve segments will be deformed versions of those line segments, right? These line segments will be taken and will be deformed according to the bending of these polygons, right? And this essential geometrical construction. So you want to get points on the curve segments. They are here, invisible at this point, right? Here's the curve. And you want to evaluate it somewhere between U2 and U6. All the curve points are between U2 and U6 on the parameter line. So now let's take a particular value and see what has to be done. Okay, let's say I pick this guy. I pick a value between U3 and U4. I want to evaluate the curve for that value, and I call it U bar, okay? Where's the point on the curve for U bar? How do I do that? First question I have to ask is, with which of the segments am I dealing with? I'm dealing with the first, third, second, or fourth. There are 4 segments. 1, 2, 3, 4. I'm dealing, well, this U value where I want to evaluate for lies in the second interval. So therefore, I'm dealing with the second segment. If I'm dealing with the second segment, I'm dealing with the second triple of control points, right? So the second triple of control points is a triple D1, D2, and D3. Okay, that's the first conclusion. I'm having a value between U3, U4. This interval is the second of all these intervals, domain intervals. Therefore, I have to consider the second triple. Let's say that. Okay, so U bar is between, what is it? U3 and U4. Therefore, I'm dealing with the second segment. The curve point, C of U bar, C for curve, is a point on the segment on the seg defined by d1, d2, d3. On the segment defined by d1, d2, d3. Okay. And now I do a beautiful geometrical construction. You just have to digest it. I consider a bunch of ratios again. I consider that configuration. I consider this configuration. And I call that step 1. And I map these ratios somewhere. I map them onto those two line segments. I map this ratio split and another split onto this line segment. Okay. So this configuration is this, and this configuration gets mapped here. Okay, that. All right. What do I do when I have two new intermediate points? I connect them. I get a new polygon. And then if there's a step 1, there's probably a step 2. And yes, indeed. And then step 2, I do the following. I consider this length. And that's where my evaluation location is, right there. And I map this ratio onto that line segment. So I get then that point. And that will be the curve point C for this particular value u bar. What has happened? Well, I've taken the original points. Again, they have superscripts 0. They are of generation 0, just like the Bezier case, Bezier curve case. And now, from the original points, I've constructed next generation points. Okay, so they are of generation 1 and generation 2. This is step 2. And that is also the last step in the quadratic case. And I give them names. So if this is D10, then I call this D11. I call this D11. I call this point D21. And the last point is of generation 2, and I call it D12. Okay. Geometrical illustration, how that relates to the parameter setting, the knots, and now I can write it down as a scheme. And from the scheme, I can deduce the algorithm, which again will be a double loop. Why a double loop? Well, you already see that. So, what have I done here? I have taken original points and computed new ones. From 3, I compute 2. From the 2, I compute 1, right? 3 to 1. That is the same, same triangular scheme that we had on the board before. So, what is happening here? I use this point D10, then I use this point D20, and I use this point D30. And I combine them somehow. And I combine these, and I get new points. I get this new point D11, D21. I combine again, and I get the curve point D12, which is the curve point C at U bar. Okay. And as I said before, all you have to understand in this class is what type of interpolation? Linear. Okay. When you look at these ratios and you map them onto these line segments, it's always just linear interpolation. Huh? It's always convex combinations of these two endpoints using ratios that are given by these knots. Okay? In linear interpolation, to get this point, the right point gets multiplied by the left length, and the left point gets multiplied by the right length. Huh? That's always linear interpolation. 2 points, point in between. Point in between is something times left point plus something times right point, and always using the ratio in the opposite order. So, what is going on here? This point D11 is something times D10 plus D20. I consider this entire length from U2 to U4, so I have to normalize by U4 minus U2, U4 minus U2, and then D10 gets multiplied by the right length, which is U4 minus U bar, U4 minus U bar, and the right point gets multiplied by the left length, which is U bar minus U2, U bar minus U2. Okay. Again, very important to understand this trick. Now how do I get this point, d21, from d20 and d30? This point is something times left point plus something times right point. And the left point gets multiplied by, well, this length, which corresponds to this. And the right point, d30, gets multiplied by this length, which corresponds to this in the parameter space. So now I have to normalize over u5 minus u3. So this one here is divided by u5 minus u3 divided by u5 minus u3. And left point gets multiplied by the right length, u5 minus u bar. u5 minus u bar. And this one then has to be u bar minus u3. Okay. In the last step, I take these two intermediate points and do linear interpolation again. This step. And I only consider one domain interval. And I have to normalize by the length of this, which is u4 minus u3. So divide by u4 minus u3. Divide by u4 minus u3. And left point gets multiplied by the right, which is u4 minus u bar. And right point gets multiplied by left length, u bar minus u3. Okay. That's it. So this is a triangular de Boer scheme. Triangular de Boer scheme. And if you were to do this for a bunch of values between u3 and u4, bam, 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 you would get a bunch of points on that segment, right? So the segment, I haven't drawn it, but the segment will look like this. This is the segment. Right? And if you evaluate for more points, you get a bunch of points on this. Okay. So that actually captures the essence of the de Boer algorithm. That's all there is to it. Okay? This geometry, these defining parameters, a particular knot sequence, and then this way of combining the original control points and these intermediate points that come out of this recursive definition. All right, let's do one more example for the cubic case, and then I throw the double loop onto the board. This is a double loop, right? For all columns do, for all rows do. That's it. You only have to see how these indices change there, right? That's it. The only trick or the only challenge for you is taking this particular example and seeing how this has to work for an arbitrary order k and for an arbitrary value of u bar and so forth, okay? But I will give you that too. So now let's do a cubic example. A cubic example is nothing but k equals 4. Okay, k equals 4. I want to do a simple example. K equals 4. 4 control points define one segment, D0, D1, D2, D3, D4. And so how many segments will I have? I will have 2 segments because I can construct 2 quadruplets. So I will have 2 domain intervals. And in the case of k equals 4, I have to introduce 3 additional knots to the left. 1, 2, 3. And I have to introduce 3 to the right. Okay, so the domain will consist of 2 domain intervals, which will consist to the 2 curve segments. So the numbering has to be U0, U1, U2, U3, U4, U5, U6, U7, and U8. And now I want to evaluate somewhere. Okay, let's make it interesting. So I evaluate somewhere here. I want to evaluate in the second interval. This is my U bar. Okay, so again, geometry first, okay? These guys are of generation 0, so they get the superscript 0. And now the first thought, again, is the following. I am dealing with what segment? I'm dealing with segment number 2. Why? Because its evaluation value, u bar, lies in the second of 2 intervals, domain intervals, right? That's the first point. If I'm dealing with the second domain interval, that means I have to consider the second set of 4 consecutive control points, meaning that the control points I have to consider now are these, D1, D2, D3, and D4. Right? I have to consider these and only these. The rest doesn't matter. Okay, now in the case k equals 3, I was considering 2 intervals in the first step. Now I have to consider 3 intervals. So first step, I will have to somehow consider this configuration, and this configuration, and this configuration. And we'll call this step 1. Where will I map these ratios or these configurations? I will map these configurations 1, 2, and 3 onto segment 1, 2, and 3 locally. Okay, so when you look at this, interval, interval, interval split, it maps here. Interval, interval, interval split. The next one is interval, split interval, and interval maps here. Interval, this split point is here. And then the last one is a split interval and interval, interval maps here. That's what I have. I have 3 new points corresponding to this the evaluation location. I give them names. Okay, how do I name them? This guy will inherit the subscript of its left neighbor. So this guy is D1 of generation 1. So this one has to be D2 of generation 1. This is D3 of generation 1. This was the first step. Intermediate points are always connected. We know that by now. So here's the connecting intermediate polygon. If there is step 1, there is step 2. In the next step, I will consider only 2 neighboring intervals. Which ones do I consider? This, this, and this. So in the next phase, I take this configuration and this one. And we'll call this step number 2. Where do these configurations go, these ratios? Well, they will go into these new intermediate line segments, okay? Always the same. Interval and the split interval gets mapped here. There. And here, again, it's a split interval, and then the interval gets mapped here. Okay. 2 new intermediate points of the next generation. So this is left neighbor as D1, so this is also called D1. This will be D1 of generation 2, so this one will be D2 of generation 2. 2 new points give a new line segment. Here's a new and last line segment. Okay, 1 last line segment, 1 last step, and now I only consider this particular interval and how it is split by the evaluation point. So the last step is here. Same location, I call it step number 3. Step number 3, I map this ratio onto that last remaining line segment, and that will be the curve point. And that will be point D1 of generation 3, which is the curve point at u bar. This is just 1 point on this particular cubic segment. Where is it? Well, it lives somewhere here. Okay, and I only evaluated it for 1 point on it. Again, this is the defining information, and I put on the board the geometrical construction. Now, what have I done there? I have applied repeated linear interpolation. I have done linear interpolation once, twice, 3 times, 4, 5, 6 times. That's it. I have done linear interpolation 6 times to get all these intermediate points. Now I can do the scheme again, the triangular scheme. All right, so let's do that. So the ones of relevance were D1, 0, D2, 0, D3, 0, and D4, 0. and I computed combinations. Okay, let's just do it for some of these points. Let's compute this point, d11, which goes here, d11. d11 is based on this construction, so I have to normalize over this length, u5 minus u2, u5 minus u2, u5 minus u2, left point times the right length, which is u5 minus u bar, u5 minus u bar, and the right point times the left length, which is u bar minus u2. Okay. So this one will be d21, and this one will be d31. Why don't we also put it down for d31? What do we do for d31? For d31, we have to consider this configuration. So we have to normalize over this length, u7 minus u4, u7 minus u4, divide by u7 minus u4. Here, right length is u7 minus u bar, u7 minus u bar, and this one has to be u bar minus u4, and so forth. And we compute more and more points, d12, d22, and the last one we will do, just for fun, will be point d13, which is a curve point. What do we do in the last step? Last step, we only consider this interval, so we have to normalize over u5 minus u4, u5 minus u4, divide by u5 minus u4, and we multiply by what in the numerator? The right length is u5 minus u bar, u5 minus u bar, and then u bar minus u4. And the rest fills in similarly. So at home, what you really have to do again and fully understand and fully appreciate are these two examples. Okay, the quadratic case is a cubic case, and from there everything generalizes to the algorithms that I put on the board. Okay, that's actually what I gave you in the handout. To write this down as a double loop, and it becomes this wonderful, beautiful double loop, very simple. But if you do not have an appreciation, understanding of the geometry where it all comes from, then that double loop is meaningless, right, for you. And you wouldn't be able to debug it. You can only debug it and understand it if you understand the geometry. So now I actually will put the essence of this de Boor algorithm on the board, which you have in your handout, actually. So you do not really need to copy this. You have it already. So this is the de Boor algorithm, the fundamental algorithm of this class, the Boor algorithm in pseudocode form, right? For the algorithm, what is given? Now we can just talk without figure. Given is k, the order, right? Given are a bunch of control points, d0 up to dn. And then the sequence of knots, how do I say that? u0 smaller equal u1 smaller equal u2 smaller equal bam bam. The last one is u sub n plus k. Okay. Last index is n plus k, very important, n plus k. And of course the location where you want to evaluate. U bar, that's the evaluation location. And this u bar has to be in the domain between u n plus 1 and it's greater than uk minus 1. Okay. And the output is a curve point. The output is a curve point, C, at u bar, curve point. All right? So now the whole thing becomes just a double loop, and that's a loop I can never remember. So the first thing is to find out with what interval you are dealing with. So you find an index I such that this particular value u bar lies between the interval ui plus 1 and ui. Right? You have to know that you are dealing with this particular domain interval and with a certain set of control points. Once you have determined this particular index I, then you have to do this double loop, this triangular scheme. And the double loop is very simple. And it looks like this. It says for j from 1 to k minus 1, the order k minus 1, do, that is essentially the different columns in that scheme. And now you do the same for the rows for, and I call it I from I minus k minus 1 to capital I minus j, do, and now I just put on the board this particular step for linear interpolation, and that's all there is to it. We compute dij as a linear combination of two previous points, that is dij minus 1 plus something times di plus 1, j minus 1. And we use the ratios that are used in these examples. In the general case, they look like this. ui plus k minus u bar divided by ui plus k minus ui plus j. And then the other ratio is u bar minus ui plus j divided by ui plus k, I plus k minus ui plus j. So this is the fundamental formula in this double loop. And then in the end, we just return the result. And so I just say, what is the result? Third, return this element in the lower right corner of the scheme. And that is just element d sub capital I minus k minus 1 super k minus 1. And that's the result. And so all this geometry, all these illustrations, all these linear interpolations, they boil down to a very simple double loop doing the same type of linear interpolation over and over again. Okay? So that is very amazing, actually. Thank you.
The preceding program was brought to you by UC Davis on iTunes U. Please visit us at itunes.ucdavis.edu.